Hello, my name is Jonathan Cerbaro. I am from Team UTBots from the Federal University of Technology, Paraná, Brazil. And I will present here a tutorial for the retrofit of the Mitsubishi Master RV-M2 serial manipulator. And we'll talk also about how we can describe the structure in a URDF file. Actually, how we can describe any robot in a URDF file. So this tutorial will follow a summary. First we'll talk about the structure of the manipulator, how it was found, how it's famous for, then a bit how we made the retrofit, how we opened the structure, how we found the sensors, and how you can find anything you want on any robot. So this will be about our robot, about the RV-M2, but the process of retrofitting can be done for almost every structure, given that you can open and find the wires and pins. Then I'll show how we made our ROS network, how we organized the topics, how we made our custom message, how we programmed the microcontroller. Also, a few tips on how to make a better control strategy. And then I will show how we can organize a URDF file and exactly what it is a URDF file, so you can use on any robot. So this will be a specific tutorial, but it can be generalized for other cases. Well, first, it's a serial manipulator. It's a node model. Our unit, since for what it says in a tag on our robot, it was made in 1998. It's famous from the Jurassic Park movies. Most people didn't saw him, but it's in the movie. We'll see a snapshot from the movie in the next slide. It's a very strong and robust robot. It's precise, but since it's old, it lacks technology for today. The first problem that it has is the ROS compatibility, but don't throw that away. You can retrofit it. You can add this technology that is lacking. This is the robot. On the left is the scene where he appears in the movies. He is the robot that is turning the dinosaur eggs. And on the right, it's our model. This is how we find him. When we acquired, he was not on his best situation. So we had to open and pull a little wires and make it look better. So we'll see him open on the next slide. For a first moment, I will say that he has 5 degrees of freedom, 5 joints, revolute joints, and 1 grip. He has brakes on the joints 2 and 3. You will see that the gravity is a little harsh on those joints, so they need a brake. All the joints have limit sensors from both sides, so it doesn't collide, and we can know when this limit is reached, so we can act on it. As I said, it obviously doesn't have ROS compatibility because it was built way before ROS even existed. So we can fix it. This is him on the surgery table. We open the part, we pull the wires, we follow the sensors, and we found how it works from inside. Of course, we had a little help from the user manual. There is a few documentation available, but it is mostly hard work from following the wires with the multimeter. It probably will be like that for every structure that you want to retrofit. You need to know where the wires come and go, where the sensors are. So this is him from inside. As we can see, the motors have encoder. From the encoder, he can know how much each joint has rotated. The reference position from the encoders can be achieved by the limit sensors. Every joint has two limit sensors, one from clockwise and counterclockwise rotation. As you can see here, it's also a limit sensor. And they all have, it's basically zero processing here. It's just connections, it's just wire. There is a few boards in here that just make the connections so the cable can go all the way down. And down here, there are just two little boards for some processing, some noise cancellation. And the connectors go up for the outside. So this is very convenient for us because we can do this. Those are the guts from the robot. We rip the guts apart, and these are just the only two boards that matter for the controller. So this is the original connector. This connector originally it was used for an outside controller from the original model. It is not necessary anymore because we followed all the way down the wires and found those pins. We attached those pins ourselves, and we found out what every pin does just from following with the multimeter for the short circuits and a little help from the documentation. And we found that some of these pins are the limit sensors. The encoder, it's a quadrature encoder, so they have two pins each, and the 5 volts power supply. And instead of just using the original connector, we use the flat cable, and every wire we just connected from the inside of the robot. What basically that means is we hacked into the robot. It doesn't matter what the original controller did. We are taking the information straight from the inside of the robot. From the other side of the board are those connections. You can see this blue connector is back there, so it's under this table, under this board. I mean, this is a very conventional connection because all the motors goes here and the brakes. It's just it doesn't say on the board, but you can follow with the multimeter. Those pins are the motors and the brakes, both sides, and the positive and negative from the brakes. So we can just use those wires and pull then outside, pull the information. Use the information, right? Directly to our microcontroller. So after you manage to find this information on every robot you have basically made this structure open source. You have access to all the information. This is basically how you start the retrofit. Where do those wires go? Well, you can use wherever you want, since you can manipulate and program it. This is here where it becomes open source. This is one way to do it. This is our way to do it. We use 3 Arduino Mega boards. Each Arduino board has a H-bridge. Actually, it has 2 H-bridges, so there are 6 in total, 5 for joints and 1 for the grip. We added a relay board There are 4 relays here, but we are using only 2 for the brakes. The entire system is fed through a power supply, 12 volts, and the USB hub that goes through the computer. All the information from ROS network is processed via this USB cable. The Arduinos are the ones who make the PID control of each joint. Each joint has an individual controller inside the software, inside the firmware on the Arduino boards. But it will be truly open source and truly retrofit if we can connect a ROS network to it. So, given that all the information from the sensors of the robot and all the control for the motors are connected to the Arduino, we just need to control the Arduino boards from on the way we want, and the entire structure will be open source for us, and we can attach any new technology we want, given that it will be controlled by the Arduino. So this is the robot today. It's fully recovered from the surgery. It's fully functional. We gave it a little color so it looks better. But we need to actually make it work. So since we used Arduino, we want the processing to be as fast as possible. So how do we make Arduino work with ROS? First of all, we want to make the messages exchange from the Arduino to the computer as little as possible, so we made our own. This is the custom message we make from ROS. Of course, we are assuming some basic understanding of the ROS usage, so we can talk about that in a 1 hour or less tutorial. And if someone doesn't know something about how we make custom messages on ROS, we can provide those files, we can provide the help needed. But in a first moment, we created 2 custom messages to make the communication. First, a set point, and then a status. The set point is how we send the position we want for the joints from the computer to the robot. The status message is how the robot responds, actually how the Arduino responds, so we can visualize the information on the computer. So we have 5 floats for the setting of the joints. Those are angles in radians. I mean in degrees notation. We prefer to use degree notation here. A Boolean information for the grip, so it's just open or close. A Boolean information for emergency stop, so it is emergency stop or it isn't, so it's just a Boolean. And a go home variable. It's not a Boolean, it's an integer. Why is that? Because we decided to implement here 3 options. Either go home, it's 0, so it does nothing. If it's 1, go home means the robot will go back to its position. This is home position, it's a reference position. So if go home is 1, then it will restart to this position. But if go home is 2, it's just a troubleshooting. Sometimes the robot may be lost for various reasons on any task. So if go home is 2, it will go home for its reference position and repeat the last command. So it's a retry, right? And the status message, for every loop that the controller does, it will send a status so we can monitor if the which joint has which set point, how many pulses the encoder has count, how is the error, how is the velocity, the output, how long is it taking to make a full control loop, and if it is done, is true, then the joint specified here is inside the tolerance. So this is just how we make those are the fields that we want, the commands we want, the information we want. But since this is a custom message, this is totally open for your situation, your case. Is just to show how easy it is to make the robot work as anyone wants. Since we are using custom messages, it's not bad to remember that our CMake list must have the message generation package. We must indicate the .message files, and we need the message runtime package. Also in the package .xml, we need to indicate that the generation and the runtime message will work in the build and execution. So it will work with custom messages. Since some people never use the custom message, it's not bad to remember that this is necessary. But remember, when we are programming on Arduino, we are using C language. It's just a C language, but for the microcontroller. And to do that, we need to run some nodes on ROS that will allow the Arduino to talk with via the USB cable through ROS. So first we need to install those two packages. Is a ROS, the distribution you are using, ROS Serial Arduino and ROS Serial. You need both of those packages. Distro is the version of ROS you are using. We are using ROS Melodic, but I believe any other version is possible to put here. And with those packages installed, you can run this ROS node on Serial Arduino called make libraries. And you need to put a little dot here. This is a first argument of the make libraries.py. It means to search for every package for custom messages. You can specify the path here, but we just use the dot, so it creates for every custom message. Why is that? We just created a custom message, but there is no C library for it, and we need a C library to program on Arduino. This package is made from them exactly to automate this process. So you can run this and the C library will be available. You can just use the include header in the C file and it will work instantly. Also, for every Arduino project using on Linux, not just ROS ones, you need to add your user to the dial out group. So this command will allow the Arduino to be executed. Then, to start the Arduino node on a USB file, on a USB port, you need to use the serial node.py and make 3 copies of it. The original example that you download when installing the ROS Serial Arduino package will have this serial node.py, but we need 3 of them. So we just make 3 copies of it. We do a ch mod, so they are now executable. Remember, just give another name. And we just have to run this serial node.py as a normal ROS node, and they will all connect. But the first argument must be the USB port that the specific Arduino is connected. For the 3 nodes that we are running, each one you will have one USB port. You need to know which door is, which port is from your device. Another option here is to just open the file and change it manually, because in many cases it's always the same port. I will show you how we can do this here. We have it open. This is the Arduino.py node. It's their code. We can just copy. We change the node name. We have to change the name of the node and the file. It doesn't need to be the same, but if you have more nodes with the same name, you will have problems. And this is the default USB port, USB device that this node will connect. This needs to be the this needs to be the Arduino port. Every node will have their own default port. If you don't specify this, then you have to write it on this command. If you don't write this argument, it will use the original, the default port. This is exactly what I said, so I will go to the next slide. Now we can build a launch file. This is an example, right? I'll make this big right here. Oops, sorry about that. Here. This is the launch file we've made. It just run the 3 Arduino Pi that we created. They are on the same package, but each one with its own name. We also made a angles node. This is not part of this tutorial, but it's just a common node we made for sending the angles to the Arduino. In a moment I will open the controller files for you to understand how we made them to receive those commands. The important part is the receiving part. The sending part will be entirely dependent on your application. Okay? So here is what we will see in the code now. The control strategy is entirely inside the Arduino. From the outside, we just send the angles and the commands and the reset and retry commands. But the entire control strategy is inside the firmware on the Arduino. So we use the PID controller on each joint. For every robot, the PID will have a set of constants or a control strategy entirely dependent on your structure. So I will show mine, but it's not always the same. And we will check the code now. So this is how we program the firmware on the Arduinos. There are a lot of functions here. It's not worth to go step by step. I will just talk about the main steps of this controller, and those files will be entirely available. You can always ask for them, and I will mail you them. They all have the comments on each line of code, so you can always understand what is going on. It's very educational. So for the ROS to work on Arduino, you need first to include the ROS.h header file, and those two files are the ones that are generated. Those are our custom messages. It depends on what you created, but this is our case, as I showed on the last slide. And those headers were created with the make libraries node that we executed. Those files are located here. the Arduino, your workplace for Arduino, libraries, roslib, move master message. This is our package. It will create a file with the name of your package, and inside the .h for the messages. This file is generated automatically. You don't need to do anything here, and you can just include the header on your Arduino file, and it will work. Here are just some constants. This is just for make the H bridges work. The enable, this is just some constant. I will not go from one to another. The controller constants, it's not very big deal here. I'll just go to what matters for the ROS configuration. This is how we program the Arduino to connect to ROS topics and to send and receive messages. First, we need to start the node handle, exactly how we will do in C. We created the publisher. This code in particular is for the joints 1 and 2. There is another code for joints 2 and 3, and another for 5 and the grip. They have their little particularities, but they are basically the same code. So we need a callback function in order to receive the commands, right? The angle information, and then you create the subscribers. So they will receive on the set points topic, and you use the callback message that we will see below. This is just the setup. We enable the outputs and the inputs. Very important to know that sensors are inputs and H bridges are outputs. Be very careful to not reverse those things. The enables must be high, obviously. But if you reverse something, you may cause damage to your board or to your robot. The encoder information, it's an input, so it must be an interrupt. There is no other way to count the encoder pulses other than make them an interrupt. And this is a small problem, but it's a problem. Since Arduino is a microcontroller, the only programmation we can do in it is serial programmation. There is no threading. There is no multi-threading, no parallel programming. So the interrupt will pause everything else that is happening. It will pause the timers, it will pause everything. So the time we spend on the interrupts must be as small as possible, as little as possible. So I will show you how we can do the encoder counting in one line of code as fast as possible. It will be at the end of the code. I will be there in a moment. And in the setup function of the Arduino, we need to start the serial and start the node. It must start here before we start the subscribing and the advertising. Those are the commands for the ROS to start publishing in the topics and start reading the information on those topics. This is just some other configurations. It's very specific for our case. As I said before, I can't go line by line, or else this will be a 5-hour tutorial. And the void loop must start with a spin once command. This is another situation that is necessary just because it's a serial programming. Since the Arduino node cannot constantly communicate with the ROS network, there need to be once in a while this spin once code command, because if it gets stuck in a while loop, it may be too long since the last time it communicated with ROS. So ROS will not see anything, so it will disconnect this node it will time out. So every once in a while, use the spin once command. The information of if ROS is connected or not is made through the connected command, connected method, but different from the C command, it must always come after the spin once. If you run this command before the spin once, it will give you an error. So it must be this way. Here we just publish the information. It's just a function to write the message to publish. I will show it later. There is nothing special here. If there is a necessity to reset the program, it will reset. So the first thing the structure does when it's energized is to reset the joints. The encoder is not a potentiometer. It doesn't know where it is when it's power off. So the first thing to do is to reset the structure. This is just our control loop. It's just a digital PAD, nothing special here. It's bound to the minimum and maximum PWM values for the output. So it's from a minimum that we set, that it's minimum to make the joint to rotate, and a maximum of 225. What we've done here is just a reading from the limit sensors. Maybe the kinematic calculations can send you through a angle, joint position, that can't be physically reached by the structure. So if a limit sensor is hit, then the motor will stop. There is a command for it to stop. Else it will just go clockwise or counterclockwise, whatever it was going before. So always making a digital read from the limit sensors, always. Else you can have mechanical problems on your structure. It will do our loop control until it's until it's below the tolerance you can set. It's nothing special here. And since this code is for joints 1 and 2, there is one loop for joint 1, then it repeats for joint 2. Everyone with their own specifications. This also controls the limit of the joint. And here is how we publish information from the Arduino to ROS. The custom message we created is here. We just fill the fields with the information we want. And when we have the publish and we do a spin once, it will appear on the computer. You can visualize, you can do whatever you want with it, both for joint 1 and joint 2. The callback is just the same, just the opposite actually, because you could just receive the message. I do here a little conversion from degrees that are received to pulses. That it's the only thing that the robot knows is how many pulses it's counting. It doesn't know how many degrees. It knows the pulses of the encoder. So there is a constant for conversion. If it has an emergency stop request, it will emergency stop. This is, I won't go into in details on this one. It's just a go home function. The only thing it does is start the motors to rotating in a given direction until the limit sensor is enabled. So once the joint knows it's at the limit, then it has a reference position so it can go wherever it wants. This is the default process when the system starts. So it knows where it is. For the joints that have brakes, the brake is not analog, is a digital brake in our case. It means that you can't just soft brake any joint. They are either at brake or not. So the brake is off or fully on. It's like a handbrake. It will fully stop the joint. When you need the motor to stop, the brake is locked, so the gravity won't push it down. When you need to move the joint, you need to release the brake. This is how we made the reading on the encoder. This is the interrupt. So this must be processed as fast as possible, mainly because there are too many interrupts when the motors are rotating. Every encoder pulse will make the code to fall in this interrupt. So, how we made this as fast as possible? The quadrature encoder, they have two outputs, two signal information. One of them is the exact same information as the other, but a little delayed. So to know, we don't want to know just how many pulses we are counting. We want to know the direction of rotation. So we just read one of the pins. In this case, we called encoder 1A or 2A. And when there is a rising edge on the A pin, then we read the B pin. Think with me. If the A pin is high because we have a rising edge, if A is high, then we look at B. If B is already high, the direction is 1. Let's see, clockwise. If B is still low, that means in the next instant it will be high, because B is just a little delayed from A. So if B is already high, one direction. If it's low, it will be high soon, so it's the other direction. So we decrease or increase the counting of the encoder based on the other pin. We interrupt with one and count the other. Okay, and this is just a switch case for the H bridges. This is just a regular motor go function, and basically that's it. With this code, you literally bypassed all the original controller from Mitsubishi or any other structure you have. The main points here are the custom message and how you configure the ROS topics. With those information, you can do literally whatever you want inside the ROS possibilities. So what we did until now with this tutorial, we opened the robot, we understood where the pins and sensors come and go. We programmed ROS serial nodes for the Arduino. We programmed launch file. We programmed a firmware for joint control, and basically hacked into the system of the robot, and now it is completely open source. But sometimes you may need to visualize the robot in a virtual world. It depends on your application, but sometimes you don't need to simulate the entire physics of the ambient. You need just a simple visualization. And for ROS, the perfect visualizator is the Rviz tool. It's native from ROS itself, and it allows us to build a transformation tree that simulates the robot, and we can just connect everything to it. So how we actually do this? Well, there is a language. It's actually just a XML file, and it's the description of any kind of robot using its parameters. It's called URDF. That means Universal Robot Description Format. You need first to understand how a transformation tree works, or a ROSTF, how it actually works, how the links and joints connect. I mean, it's better to know that previously, but I will show you how it's done. And then you use the kinematic parameters of the robot to create this file, and you can attach 3D meshes. I mean, anything you can project on a 3D in a 3D design program, you can use on Rviz, attach it to the ROSTF links. So how it is done? I will show it with the code. It's much easier to show the code. And this is the robot we are trying to simulate. Notice that this is our current configuration. We attached a 3D printed camera support. It's not part of this tutorial to talk about the visual processing we have. This is a RealSense depth camera. It's currently on work. It will be used to manipulate objects with this grip that we also 3D printed. This is the grip we attached. So the robot originally was this structure until this part. This is joint 5, and this is what we attached. So we want to simulate in a virtual world this entire structure. Okay, so how do we make Rviz to understand those formats? Well, first we need a transformation tree publisher. This is very default. I will show this just because some people never worked with a serial manipulator transformation tree. This is just a set of links and joints that are attached to each other. And this code is very, very default. It's very common, but I will briefly go through it. You need to include those libraries, the joint state and the transform broadcaster. Those are ROS default. You don't need to do anything here, just include them. And we create a vector. We resize for the joints are 5 and the positions are 5 too. So we just made a vector for them, and I gave them the names, very obvious names: joint 1, 2, 3, 4, and 5, and their position. I actually set them to 0, but joint 1 I slightly increase for each loop, and joint 4 too. That's just an example, so we can watch the robot rotating. You do whatever you want here. Those are just variables. You just need to set the angles here, and every time the ROS does a loop, this will happen. And the transformation will be published to every node. This is the orientation part. I am not using it right now. I'm just setting it to 0, but the orientation also may be important in some cases, in the majority of the cases actually. So how do we control those joints, and how do we visualize them on Rviz? First, I created here one of the links. I called it origin. It's literally the origin of the whole system. And I attached a child frame here called base. The whole robot will start at base. I define this here. This is my situation. You can adjust that to your case. But what I want here is that the URDF file to start at the base frame, and everything I will see on Rviz will be in relation to the origin. Sometimes the base is not the origin, so the robot can move freely on the environment. Once you say this is a CPP file, obviously you have to do a cat make, just as a regular node on C. You must compile it. And then we have the URDF file. First, what does it do? The URDF file will have in here the joints and links with the same name as we did here. As here we actually the links doesn't matter for this case, but since I gave the joints those names, when this node is running, the URDF file will understand what we are talking if we specify the joints here. So how this file works? First, we need to give the robot a name. We use this tag. You see this is very similar to a common XML file. This is actually XML files, the extension, but the tags we use here are specific for this language. First, we need to give the robot a name. Okay, we'll close this robot tag at the end of the file. Okay, the first thing we will describe here is the first link. It's called base. Why I'm starting from this is there are some catches here that I want to go step by step. First, why we start with a link? Every robot will start with a link, not a joint. It's easier that way. You see why? I give the name base. Okay, why is that? Because the child of the origin is base. I specified that here, so I will start here with base. Now the URDF file knows I'm talking about the same thing. Fun thing about links is they don't actually matter for calculation. Unless you have some specific application, it's your case to have some utility for it. But here they are just for visualization purposes. They are just, the skin of the robot. So first of all, since base is a child link from origin, as I stated here, I have to say where the object will appear with respect to the origin. This is the visual information. As you can see, it starts here and ends here, and everything inside is just for visualization purposes. So the origin of this link will be 12 centimeters from the x-axis of the origin. Here is 0y and 0z. This is the position, and this is the row, pitch, and yaw for the orientation. This is important. You'll see why in the next joints there are some catches here, especially on the orientation. But this just tells the Rviz, the visualizator you are using, where to put the origin of this link. But it will be the origin of what exactly? Here you can use this geometry tag. This is the actual object that you see. And here's the catch. You can use many tags here. You can use a cylinder, you can use a sphere, you can give the radius, you can use a cube, you can use anything. But we are using a STL file. This is the catch. We have a 3D model for the link 1, for the link base, and we made it in a STL file. I will open here for visualization. This is our 3D visualizator. Ignore this one for the moment. I will come back to it later. This is the base of the robot. But it depends entirely on how the developer project here. This is a SketchUp visualizator, And what I want to show is this has reference frames. This blue one is the z-axis, the green is the y-axis, and the red is the x-axis. So how this model will appear on the visualization? Sorry about the interruption. How this model will appear in the visualization is dependent on how we configure the axis on the 3D modeling. So this model has an origin and it's way over here. So if we use the file saved, I'll just delete this one so it's easier to understand. So if we save the STL file like this, is very different than we save it like this, because the URDF file will understand where is this origin. Also, it's very, very different if we save it like this. It will understand the orientation. It's a problem. It depends on how the designer made the structure. And I have two here because I will show something later, but we need one file for each piece. Those pieces must be saved on two different STL files. Okay, that's exactly because we are specifying the file for this link right here. So since this file was originally saved with the exact origin on 000, and I need it to be 12 centimeters on the x-axis, I am specifying here. This is just for visualization. If you just change something here, I mean, if I give some rotation here or whatever, it will just appear different, but it will not influence, it must not influence your kinematic calculations. Okay? So, until now, there is no joints here. There is just one base link. Basically, we have the base of the robot. We will have this piece showing up at 12 centimeters from x-axis at the origin. From the origin, I mean. Well, after the first link, we need the joint. So here is how we describe a joint on URDF. You must give the name, exactly the same name we give on the TF publisher. This is joint 1. Joint 1, and we must say here the kind of joint. It is either revolute or prismatic, or it can be fixed too. We will see an example of fixed joint on the next steps. But joint 1 is revolute. So just say it here. And the first thing we need to know about a joint is what is the axis of rotation. You can specify the XYZ axis. As some of you may know, in robotics, we want all the axes to be unit length. So we avoid doing 0, 1, 1, for example, or whatever, 0, 0, 2. We avoid that. Here, we are saying that the axis of rotation is along the z-axis. Why do we need to say that? Because I don't know exactly why, but for the Rviz and for this file, default axis is the x-axis. And on cinematic calculations, we don't do that. We always use the z-axis as the rotation axis. There are some cases that's not true. If you are using successive screw methods or anything like that, but for the default Denavi-Hartenberg method, the z-axis is the rotation, it's the degree of freedom of revolute joints. So we need to specify this in order to work. I will show later what happens if you don't do that, but that's for the visual part. Here, the origin, it's very different from the origin of the link. On the link, we are giving the origin of the mesh just for the visualization. Here, we are giving the origin of the joint on the transfer function. This is very important. It's the Denavi-Hartenberg parameters, the X offset and the Z offset. Those values are for this model specific. Your model will have your parameters, of course, and the joint will always have one parent, one and only parent. So this joint is attached to the base link. The joint always have one parent link, okay? And it can have more childs, that's no problem. But this case, since it's a serial manipulator, it have one child, it's link 1. So a joint will always be between two links, one parent and at least one child. It can be no child too, if it's the end effector, of course. But in this case, we have one for each side. Here you can determine the dynamic components. You can give a lower limit and a upper limit for the joint angle. You can have an effort constant. It's used to simulate mass, inertia, a velocity limit, so it can move faster than that. There are a lot of different tags you can use here. So just for simplification, I will just leave these ones here. Since this is just a kinematic simulation, they don't actually matter for the moment. But this is a very, very long list of things you can put in this tag. So we have a link attached to a joint. Now we have a joint attached to the next link. Something I forgot to mention, the material tag. This is also for pure visualization. You can give a material to it. You can load a texture in the exact same way as you did for the mesh. In our case, I'm just painting with the color I want, so I must give the name for the material. It's just color, whatever. And I specify the color using RGBA code. So red, green, blue, and the alpha. You can just use a online editor for the color you want, and it will give the code. It's from 0 to 1. It's a percentage here. Okay, so the same thing I do for the next link, but here's the first catch for this link. I said up here that link 1 is the child of joint 1. So the mesh will appear at the origin of joint 1, not at the origin of the whole system. So the position can be 0, 0, 0, so that the origin of this joint, or I mean the origin of the STL file, will be at the origin of joint 1. So 0, 0, 0 will be exactly here, exactly at this joint. For this one, I don't need any rotation, so the rest is exactly the same of the base. And the link 1 will be attached to the joint 2. And here's a little catch. I already showing here the link 2 also. There's a little catch here. It's the rotation. As I can see here, and I will open again the picture. Just a second. I will open the picture of the robot. As you can see here, this is the rotation of joint 1, and this is the rotation of joint 2. So I changed the visualization to this picture so we can see it better. What I mean is the joint 1, this one is here. The axis of rotation is like this. We want the joint of rotation for joint 2 to be like this. So this is what we want it to be. It can be like this, or it can be like this. We chose it to be like this. So from here to here, we rotate about x-axis in a minus 90-degree angle, so minus pi over 2. Okay, so for it to be like this, so joint 2 can be like this, okay? So minus 90 degrees, or pi over 2, it's minus 1.57, that's okay. And this is the offset on z-axis. Okay, again, this is obviously because joint 1 is here. We go z-axis and minus 90 degrees. So we have joint 2. The rest is exactly the same as joint 1. I didn't did anything here. The parent is link 1 and the child will be link 2. Here's another catch for link 2. The position will be the same position as joint 2. But since we did a rotation of minus 90 degrees here, we must look at how the STL file is. That's why I'm using both here, just to show you. As we can see here, both those joints, both those links, this is the base link, this is the L2 link, they are correct. This is the exact perfect position, given this reference here. But since in this file, joint 2 is rotated minus 90 degrees, the visualization of this mesh will also be rotated minus 90 degrees, because this is the child of this joint. So to appear as we are seeing here, we must counterbalance the rotation to the other side. That's why we are using plus 90 degrees here, plus pi over 2. This is in radians always. So if the joint is rotated to one side, the visualization link is rotated to the other because of the STL file. If this piece was designed already in rotation, there will be no problem. We wouldn't need this. So again, everything we do in the link section will always be to adapt the visualization of what we are doing. Here I give the color. In a moment we will see this color, it will be moving. And from now on, we'll just complete the rest of the robot. Every joint, every link. On joint 3, the catch is just on the visualization. Since the joint 3 is the child of joint 2, is the serial manipulator will be joint 2, link 2, joint 3, link 3. So joint 3 doesn't have a rotation, but it's child from link 2 that is child from joint 2. So the rotation is here too. You don't need to specify this, but it's rotated 2 because of the kinematic chain. So the visualization of link 3, you don't need to specify the rotation of the joint, but you need to specify the rotation of the visualization link. It will be carried here, minus 1.57, just like in link 2. Okay? This is a little catch. If you get it wrong the first time, you just have to visualize it, and you'll notice that something is wrong. You just come here and change it. From now on, joint 4 exactly the same thing. You give the axis, you give the offset, you state the parent, the child. And now in the link for mesh visualization, you don't have rotation anymore, because joint 4 will cancel this is the visualization, okay? Joint 2, joint 3, and joint 4. Now you don't need anymore, because that's how the STL file was generated. Again, it just depends on how the designer of the STL file made the file. So we just adjust here so it looks okay on the visualization. Joint 5, the same thing. Link 5. Okay, here we are at the end of the robot, but we need to attach the rest of it as no, here we don't have yet the camera support. What we want to see is this. We want to see this structure there. So the camera link, the grip link, the grip cube, I call it cube because of the shape, and the grippers, both of them. We need to insert those two at the URDF file. How do we do that? This is the last, joint 5 is the last Revolute joint. And after the last Revolute joint, we'll have this differentiation on fixed joint. That's how we do it. Instead of specifying as Revolute, we just say it's fixed. If it's fixed, it doesn't matter how we manipulate it, it won't move. So we don't need a rotation axis. As we specified here, this is not necessary. The rest is exactly the same. The only difference here is for the first moment, we are not saying that those are prismatic joints. We are just saying fixed joints. Those don't move for this moment, because I want to show how we can have two childs from a same link, and there are many ways to do this. The entire description of this file is just how we did it, but there are many ways to do the exact same thing. I mean, those frames, those mesh files can be child from the grip cube, or they can both be child from the joint 5, or they can both be child from the origin link down here. It doesn't really matter. What only matters is that since they are fixed joints, they are child from some kind of origin, and they must be specified. They just can't be two parents. How we do that is like this here. I mean, there is the grip cube, the grip 1 and the grip 2 are both childs of the grip cube. The only difference of them is the offset. This is the grip cube attached here, and we give just the offset from one side and from another, and we need to rotate the STL files to make them appear exactly like this. This is done exactly as we did before, just make some rotation. This specific file needed to be rotated from along Y and Z axis, this one too, and it will be shown exactly as we want it to be shown. Okay, but this is a lot of code, and here we close the robot tag. This is a lot of code and write and notation, but this is not fun. This is just configuration. Now we are gonna see how this actually behaves. Well, we stated here in the publisher that we wanted the joint 1 at the position 0. Do not mess this one. Position 0 is joint 1 to increase, and also joint 5. Just a little increase on every loop, so it just rotates. And we gave here the visualization mesh. How we visualize this? The visualization is made after we just launch the file. I created here a launch file that I make it bigger, larger, so it's easier to see. This launch file just will run the TF publisher. So here it opens ROS. I can see here if I give the command to print to us the TF, just wait for 5 seconds and it will show to us this one. The origin frame, the base frame, since they may be not the same, and then link 1, link 2, link 3, link 4, link 5, camera support, the grip cube, and the both kids, the both childs, grip 1 and grip 2. Okay, so the TF is okay. This is exactly what we wanted. So now we want to visualize this. How we do that? We open Rviz. As soon as you open it, it will show an error because it's not map. This doesn't have a map link, so we use origin. Okay, but there is nothing here. We want to visualize the TF, the whole TF here changing. So we go to add, and we see a TF here. Oh, it's here. This is our robot. This is the TF, the links. The joint 1 is rotating, the joint 5 is rotating, exactly as you want. But this doesn't help us very much. So to visualize the URDF file here, we go to add and use the robot model. This will open all the URDF files that are associated to the TF here. And here we have it. We can just disable the TF, so we can just see our robot model exactly as we wanted here. Joint 5 is rotating, joint 1, 2, the axes are good. Of course, we can manipulate wherever we want. It just need to publish some joint value here. We can read the values for the joints on the real robot that are being published by the Arduino and replicate it here on this publisher, so we can visualize exactly in real time what the real robot is doing. This model is not perfect, of course. It's just approximation, of course, but it does the job. So everything is working properly. But let's see what will happen if we did something wrong with the visualization. Here we are back at the URDF file. So, for example, let's say that link 2, we forgot to rotate the visualization mesh. Okay, so it's not as we wanted before. We go back here, we run the file, we run Rviz, we change it to ODOM. Of course, I could have saved this configuration file, but this is just a demonstration. Robot model. As you can see here, it's still working, but this mesh is wrong. This link is rotated 90 degrees. It's wrong. It works properly, but the visualization is wrong. As I said many times, the link mesh is just a visualization, so it's not wrong. It's not wrong in the working point of view. It's wrong in the visualization point of view. Okay, so here I'm back to the correct configuration. But what if joint 2 didn't have the axis of rotation specified? So if we don't say that, it's funnier if I do this with joint 1, you'll see. If we don't specify the axis of rotation of joint 1, it will rotate along the x-axis. That's a problem, because that's what will happen. Also, oops. There was a problem in Rust, no problem there. It auto-fixed it. So the ODOM origin, and now we see the robot model. Something is clearly wrong here. This is rotating joint 1 along x-axis, and it feels like joint 4 is stopped because it's the exact opposite rotation, but this is not correct, of course. So this kind of problem that you see when visualizing the URDF file is just some configuration. It's always some axis you got wrong. That's not big a deal. You just spend some time fixing those minor errors. As long as you are consistent with everything you choose, the file will be correct. I will put it back here because I don't want my project to be wrong, of course. And this is how you create a visualization file. This works for any kind of robot, parallel robots. Maybe parallel robots will have problems with the parent-child relation, but you can always use a bypass. And it always depends on how the STL file was projected on the 3D modeling program. So as far as we understand, those axes are important for Rviz. Okay, so with everything we saw in this tutorial, we can completely visualize and control and do whatever we want with the we are doing this with the RV-M2, but that works for every other robot that I can imagine. Okay, so this is the final version of our robot. It will have some other retrofit features like the visual computation, the depth camera. It will be able to manipulate objects on real world. It will be able to, this is a Hanoi tower that we are going to use. Once you hack into the system, once you know how to collect every information of the sensor, basically you have a completely modern robot. You can do whatever you want, wherever you are able to attach to the controller. It's your creativity, your project. You can do whatever you want. So thank you very much for watching. I hope I was clear on what I said. I'm sorry if my English is not perfect. This is not my first language, but I will be able to answer any questions you have. I am glad if you send us an email. We can help each other and make the robotic community every day greater with our collaboration. So thank you very much.